So again, I've already done this in class for the recording. I want to go back and hit the high point real quick. So this is the test exam. Is the test and the true response is number. The test number is composed of species. And I'm going to go ahead and tell you, in the past, this has been one of the most challenging tests. And the reason why is because you're not used to answering these kind of questions. You're not used to the kind of identity of it. You just got to get used to it. But it can be a little challenging test, okay? So the first one, say it again. No, not on that one. No. So number one, be able to calculate certain variables of gas using PVs as an estimate of the number of gas cells. Again, remember the big thing in this, if you kind of got this more, okay, the unit must match. That's going to be the most important part. If you don't put all of the units in it, and then your R, remember we have to use the gas R, because there are two different versions of that gas R, okay? And will you be able to use the formula too? Again, when it says use conventional round off, don't use the NPR, don't use that, okay? Use the round off. Now, number two, be able to write reactions according to temperature. Oh man, there's only a second page for this one. Decomposition in acid base. Take special attention to successive factors decomposition reaction occurs in the middle carbon. So this is where we like to split it up. So what I have here is I have two different elements here. One of them is a decomposition in the middle carbonate, and one of them is a synthesis in the middle carbonate. But do they have exact same components depending on which two carbonates come from? So if you're decomposing your middle carbonate, again, what is in it? Anybody, okay? But this has a charge of what? Plus one, because negative 2 came down from carbonate and there's nothing outside of the carbonate. So we have a metal carbonate, and all metal carbonates always decompose into metal oxide and carbon dioxide. Okay? So the second one is we use yttrium oxide plus carbon dioxide yields yttrium carbonate. Sounds weird, but what is the charge of yttrium in that one? 3. Okay? So what I'm going to do is I'm going to add a third one. Okay? So what if we have ZCO2? Now there is no such thing as Z, is there? There is a Z. I know there's a Z in there, but so is this you know what the hardest part about this is? Recognizing wait, hold on. Recognizing the fact that it's a metal carbonate. Okay, I got that right already. Recognizing that, hey, that's a metal carbonate, and that's metal carbonate. What happens as it decomposes? What would its products be? Now, why does this ZO? ZO is a peak load. Reactions are too many. Okay, so that's why it can decompose. So is that a good part there, Spencer? You figured it in chemistry. Decomposition. Okay, number two. Okay. All right, number three. Be able to compute the empirical formula if given percent deposition, lab data, or combustion. Okay? Be able to calculate carbon and hydrogen just from CO2 in water. Let me tell you what I mean by that. One is, first of all, do you agree that all combustion reactions have a basic center of this? Okay? So, say that again. This is combustion, yes. Okay? If I want to know the empirical formula of this hydrocarbon, can I tell you? And again, I'm making these numbers up. I'm just going to try to make sense. If I've got 3.20 grams of carbon dioxide and 6.90 the convention version of interactive programming. Okay? Now, I'm trying to get length out of the CNC. Trying to get to the carbonate, right? So do you agree I need to go from grams of carbon dioxide to moles of carbon dioxide? Are you cool with that idea? Now, I may not have a clue what I'm doing, but I'm going to attempt to anyway. I'm going to try to put moles of carbon dioxide here. Now, this is something that we've been seeing now. Is it possible to go from the compound to an element within the compound? Yes, that's called molecular combination. So can I go from mole of CO2 to mole of C? We can. How do we know it's a one-to-one ratio? Very good. Now, this part is the easy part. 44.01 grams. So, could you get the number of moles of carbon? Sound good? You cool with that idea? Great. And none of these numbers are going to make sense. It's not going to come out to be a perfect equation. So I'm just going to ignore them for bragging purposes. Yes, you pulled that point. 0.0. Sounds good. Now, so let's go to the next part. This part, we've got 6.90 grams of H2O. Now, I know where I have to at least get rid of. Got to at least get rid of grams of water. And I at least got to get into moles of water, right? Because I'm trying to get what out of the water? Hydrogen out of the water. Are you good with that? I can't stay here, so where does moles of water have to go? Got to go to the bottom, so I've got moles of water on the bottom. Now, how many moles of water? At what point do you go from water to just air? No. No? So your molecules have an ratio. Yes. What's the mass of water? This is the next important part. You've got most of this down. 1.1 to the minus 400. Very good. Uh-huh. What's one more point? All right. So, answer the question. Why, and we've already answered this, why are we able to get the amount of carbon out of carbon dioxide? We're going totally simple math. What math? Calculation of mass. So, do you agree that the only place that carbon was on the reaction side is right here? The only place it has ever been is in carbon dioxide. So because the law of calculation of mass, what you have on one side, you have to have on the other. Is that true? Okay. Now, the reason we can get to hydrogen is because this is the only place it is for addition, and the only place it is for oxygen, or for hydrogen is on the other. So we can determine, because of that law, what you have on one side, you're going to have on the other. Now, if we did this, again, the initial question was what's the importance of science? This is the easy part. Now, these numbers that I made these numbers up. If I'm going to give you a list, if I'm not, I'm going to take you somewhere else. What would you do from this point to get to the importance point? Combine all the small time over here, and then that has got to be the biggest point. Feel me on that? All right. So if you wanted to divide that just what I know you're doing, could you tell me what that is? Again, I made these numbers up. If it actually works out to be something, I'm going to be super impressed with myself. Really? So if you do 0.766 divided by 0.07, okay, give me a second. C2H21. So it was C1H, something almost 11, right? 10.5. So we're going to skip the 10 on that. Now, divide both of these by the smallest, and then each one of these numbers has to be within zero point 0.1 of a 1 or an I. And you treat those numbers in perimeters. Okay. So the part that I wanted to show you, we've already done this with carbon, right? We just didn't do it with hydrogen. I just wanted to show it to you with carbon. because if you look at our numbers up here, it's very easy. All right. Next one. Be able to determine the molar mass of a gas from data. So this is a new formula you've never seen. P is the same as P that anytime this is I'm going to underline it equals DRT over P. What happens? The molar mass.
All right. So I want you to write this beside this. Dirt P. Molar mass kitty cat. All good cats put dirt over their pee. Oh. It's DRT divided by P. Dirt over P. Shut up. All good kitty cats put dirt over their pee. Now, I know what you're sitting there thinking. All right, I'm cool. I got R. I'm feeling that. I'm cool. I got T. That's temperature. We're good. P as pressure. We're right on. You look at that and you go, what the hell is little d? Okay. So, what do you think the lowercase d is? Well done, Dustin. Density. So here's where it gets real funky. Shut up. That is even more awkward. No. All right. Here's what I'm fixing to do. I'm fixing to really. You guys are awful. Sir, just bring him to me. What? No. Yeah, just put him right there. I'm thinking. Stay with me for just a second. Hold, just stay with me for just a second, because I'm fixing to make a connection with you guys. My first question is, what is N? Moles. R is R, T is temperature, V is volume, P is pressure. Would you agree with that? Okay. R is R. Can you what can you get moles from and to? What can you do with it? Graham, so stay with me for a second. You with me? You with me? What is G over V? What is grams over volume? It is density. Okay? So I could circle it like this. Essentially, with different variables. You can rearrange it to get it into that. So here's what I want you to do. Tristan, go ahead. Yep. All right, let's look at. All right, let's look. You guys have it number 98, or year 98. Hold on. Maybe that's C. 98C. 98C. If you know, there should be room at the bottom to do it. I know. Hey, can I talk? Thanks. Hey. Okay. So see, when a 1.5 gram sample of compound is vaporized at 300 degrees Celsius in 1 atmosphere, the gas occupies a volume of 577 milliliters. What is the molar mass of this compound? So let's stop right there and let's look at this. So here's the deal. Notice what they gave you. They gave you a mass, true or false? True. They gave you a temperature, true or false? What is 1 atmosphere? Pressure. And then they give you milliliters. That is a what? A volume. And then all of a sudden they tell you they want the molar mass of this thing? So, now that we know about kitty cats and what they do with their pee, okay, we can now figure out what the molar mass of a gas is. Now, I know this is going to sound weird, and this is the formula that they teach you. Molar mass equals density times R times T all over P. Well, the problem with this question and this formula, do the units match that formula? No, but can you, let me say, unrearrange it to get it to what you want? Yes, okay, because density, by definition, is what? Mass over volume times R times T all over P. Now, or the other way to write it is just gram RT over VP. Now, I wrote it G over L on the top because that's technically going to be your density. But in reality, either way you do it, should you get the same answer? Because you're multiplying it by something and you're dividing it by something. However, to do it as accurate as possible, would you use the blue version or the orange version? Definitely the blue, and we're going to double check this to make sure. The reason why, because remember, we really need density, and that is density. So let's do the gram over liter first. Let's take care of it. Now, here's the deal. The problem with, and I told you to write this at the very top of the first bullet. What was the first bullet? You had to write something. The units must match. Okay? Our units must match. So here's the deal. What unit do we really want to match it to? What's the constant? R is our constant. Now, I've told you that you can pick either or R. What? Does anyone have that in front of them? Hang on. Don't say anything out loud. It's 66 point what? 2? So, based on these two units on that formula sheet, and then based on the question, which one of these R's would you use? The top one. Because the least amount of conversions is going to be best for us, right? Sir? Yes. 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 I don't like to. I want to pick. I want to pick the right one to stay with. Yes, you can do that if you want to. All right. So here's what we got to do. We need to plug these numbers in. Now, are we good with our grams? Yeah, because we're giving grams. Actually, I'm gonna do it right here. All right. So it's 1.570 grams divided by. Now, what volume unit is your R unit? What mama meters? What volume unit is in your R? Liters. What volume unit is in the problem? Milliliters. That's a problem. We need to change it. So 0.577 liters. Now R is 0.0821 latum over mole. Now I'm going to be 100% honest with you. This is the first and only year I have ever even taught students to use that other R that has Tor in it. I've always said you have to use this one. Just because you don't think, you said, there's my R, let's get everything in those right units. And I finally realized, why do all that if you don't have to? Let's play the game. Let's use what they've given us, and let's make the constant fit our needs, not make the other stuff fit our constant. Yeah, we're just making it easier on ourselves. Instead of forcing us to convert, why don't we just pick the R that's already in the units we need it in? But let's be honest, are they more than likely always going to give you milliliters on stuff? Probably. That's going to be a normal, regular conversion. If you notice, every problem we've done, we've had to convert it to liters. That seems to be a common theme. Now, temperature. What is the unit in the R for your temperature? Kelvin. How do we get from Celsius to Kelvin? 273. So we're at 300. So we have 573 Kelvin. That is hot. Well, think about 300 degrees Celsius. 100 Celsius is boiling water. That's 212 Fahrenheit. That's really freaking hot. Okay? So that's 3 times the temperature of boiling water. Okay? Now, the pressure unit in R, this is the important one, is what? Atoms. No. Atmospheres. Atmospheres. And what is our atmosphere? 1. Now, should you be cheering for that? Yes. You don't have to worry about the bottom. Now, mathematically, do you still have to show it in your work? Yes, but you don't have to worry about the calculator. So here's what I want you to do. Well, honestly, all you have to do is just plug everything on the top. But make sure you do the density first and then plug it in. So let me ask you, is the chemistry part of this challenging? As long as your units match, and as long as you plug it into the appropriate formula, this is just like basic algebra, plug and chug algebra. But the key is your units must match, and if they don't match, you're screwed. Okay? Yes, sir. No, you don't have to put lines to it. No. Yep. Hold on. That's actually a great. That's actually a great point. So let's pause for just a second. I know that we're looking at this. Guys, stop calculating for just a second. I want y'all to look at me because this is important. Because he brought up a good point. What's the question? What is the molar mass? I need a molar mass, right? So let's look at our units. Do grams cancel? Do liters cancel? Do atmospheres cancel? Do kelvins cancel? So what are you left with unit-wise? Is that molar mass? Spectacular. Does that make sense? Do you have to write that down as the unit? Most definitely. I personally prefer gram per mole because that really is the molar mass unit, just like density is grams per mole. Excuse me, grams per liter. For molar mass, yes. Not for density, not for pressure, but molar mass is grams per mole. Y'all got an answer? All right, so yeah, I know this is going to be aggravating. I'm going to erase all this. Now, let's be honest, and this was a long, long time ago. I'm going to make this more accurate for today's world. Do that for me. Never, ever, ever have I seen a recent AP Chemistry problem with one significant figure. At minimum, there's 2. At maximum is 4 to 5. Okay, but minimum, I've never seen 1. So we've got 4 here. We've got 3 here, 3 here, and 3 here. So we would use what? 3. And so it's 128. 128 what? Yeah, either way is fine. Well, that's what that took care of. No, because molar mass is gram per mole. That's the unit for molar mass. And I proved that with my unit cancellation. Guys, if you're worried about what unit to use, if you do what we did with just canceling the units and see what's left, that will make your heart feel better because you know exactly what it is. You've canceled everything outright. Okay, so does working this problem help with that bullet on the test objectives? Okay, because when you first saw MM equals DRT over P, you said, I don't know what that is. So it's about a kitty cat, not your mother. Stop. It is a derivation of Pibner, yes. What we did is we took PV equals nRT, we rearranged it and put N over V, and we took the moles and converted it back to grams. And grams over volume is gram over liter, which is density. Does that make sense? So did seeing this help? Okay. Yes, ma'am. Okay. Stop calling it that. My question to you is, how would you know to use it? And no, this is a great question, and what I'm fixing to do is really going to challenge you to think through this. Okay, if you said, so I can come back to this. If you said, okay, well, I've got grams, I've got volume, I've got temperature, and I've got pressure. If you said, okay, well, I know what to do here. I need PV equals, I need this. My question to you is then, what is the question in the question? My question to you then there, what in the heck am I solving for? Do you see my question? Is, yeah, you see grams. Okay, well, I can get grams into moles. I see volume, spectacular. I see temperature, and I see pressure, and R is always a constant. So if you really step back and look, I have all of them. What the heck am I solving for? Do you see what I mean though? That you all these are similar, but if you really think about the question, they've given you every single variable. You then have to say, well, I know that molar mass is something different than this. Okay, well, I know that molar mass can be density, R, and T over P, because density is N over V in essence. Does that help? Okay. And I know as soon as you see, okay, grams, temperature, pressure, volume, it's going to say, okay, that's the ideal gas law. But then you have to follow the question within the question. No, not the moles. Because what's molar mass? So you can't use moles. You'd have to kick it back into grams. No. It's a form of it, but it's not density. Density is grams per volume. Per volume. Per milliliter, per liter, per whatever. But molar mass is gram per mole. You with me? Okay, Tristan? Yes. Yeah. There isn't a unit. It's whatever you're solving for. So let me ask you this. I could completely change this question. I could eliminate this right here. And I could say, what actually? Did that completely change the question? Now you're solving for which part of the ideal gas law? Mass, but where is mass in the ideal gas law? It isn't. But can you get mass from the ideal gas law? You solve for moles and then kick it into grams. Does that make sense? So, removing one word completely changes the question. The molar mass is? They would have to say, what is the molar mass? Well, I see what you're saying. That does make sense now, but hypothetical. Yes, sir. Yes, sir. You don't understand it? All right. So, if I'm asking you to solve, no, that's wrong. It is the other way. So if I wanted pressure, what is it? If I wanted N, no, that's not right either. I don't like that. You can do it. I agree with you. But here's the problem. If I want P, it's wrong. It's nRT over V. It's untriangulable. Oh, my bad. All right, if you need molarity, if you need mole, if you, all right, I'm just going to throw this at you. We're not going to actually calculate it, but I just want to make sure we're on the same page. It says an unknown compound contains only three elements, C, H, and O. A pure sample of the compound is analyzed and found to be 65.6% carbon, 9 and 9.44% hydrogen by mass. Determine the empirical formula of the compound. So when we do the empirical formula, hold that thought. So do you agree that it says this right here? So it has to be C. What am I doing? Thank you. CXHYOZ. So the problem is they only give you data about two of them. Okay? I just want to make sure we're on the same page with this. They give you the percentages of two of them, and all percentages must add up logically to be what percent? 100. So you take those two, add them, and subtract it from 100. Now, again, talking. They gave you percentages. If you need empirical formula, like A says, determine the empirical formula, what do you have to do with those percentages? Change them to grams. Once you get everything in grams, what do? Convert it to moles. Once you get moles, what do? Divide by the smallest, and those numbers have to be within what of a whole number? 1/10. Okay, a 0.1 or a 0.9 or a 0, and you're good. And that would give you the empirical formula of that. Now, that's a good point. If you get a 0.5, what do you multiply by 2? Just that one or all of them? All of them. Yes, sir. Yes. The original number. Okay. All right. This one. Know how to compute the molecular formula after finding the empirical formula. All right, Justin. A minute ago, you said that we had the empirical formula of C2H21. True or false? True. Do me a favor. Can you calculate that mass for me real quick? 24.02 plus. Heck, I don't even know. What'd you say? All right. So this is the gram per mole of the EF. Now, you would actually have to calculate that. And again, I'm just making this up. What if the question then said, what is the MF if the MM is 135.69? So, my question to you is, what do you do? It's the mass of the MF over the mass of the EF, which is what? 135.69 divided by 45.23, which is 3. So then what do? Okay? So it is C6H what? All right. Okay, hang on. Guys, for a second. Mason, to answer your question, this is the setup. This is the equation we use to determine the molecular formula. Because a molecular formula is a formula. What we're trying to determine is the ratio between the empirical and the molecular. Because is the empirical formula, is that compound the same compound as the empirical compound? They're two different compounds. So what we do is if we know the simplest compound is C2H21, and that compound weighs 45.23 grams. But the compound you have doesn't weigh that. It weighs 135.69. Well, we know if we divide that out that it's 3 times the size of the simplest ratio. Well, then you take that 3 and you multiply it by the subscripts, and that gives you the actual compound that you're holding. It'll come out to be a whole number. I mean, it'll be very close. It'll be that 1/10 thing. Okay, your question. You got it? Justin. No, go ahead. Yes. 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 All right, Dustin. You have a question? All right, the next one. Calculate the mass and moles of water and the compound from the gravimetric hydrate lab. Now, we've already done that. You remember the one that we had the copper and the iodine react with each other? It's something very similar to that. But it's also talking about hydrates. Remember, if we've got calcium carbonate trihydrate. Okay? Now, check. Let me change that. Something hydrate. What you're going to try to have to figure out is how much water is in this thing. Okay. I did. I changed it. I went back to 0. Hold that. Hold on. All right. So we've already looked at this. You should have already done this, Dustin. Dude, you're making me nervous. Yeah, him. Yeah. Just it feels like you're just gonna run out of the room. All right. So this is a worksheet that you guys have had. It says that calcium chloride hydrate has a mass of 47.72 grams. After heating several minutes, the mass of the anhydrate is found to be 3.56 grams. Use the information to determine the formula of the hydrate. Now, I actually want to go a step further with this. So, first of all, would you agree that this is CaCl2 times something hydrate? Let me tell you, sir. No, that's what you've been doing. Okay. So let me take this a step further. How you could possibly have seen this? So here's the deal. Let's pretend that we were doing this actually. And I give you 4.72 grams of this. Yes, sir. This was chloride. I'm just going to change it to chloride. So let's pretend that I gave you 4.72 grams of that compound. Okay, could you hold it with your fingers? Could you touch it? Okay, and what we did is we took this thing and we heated it 4 times. Now, obviously, what are we trying to do? We're trying to get all the water out when we're heating it. Can you heat it 1 time to determine if all the water has been driven off? No, you sure can't. You at least got to do it how many times? You at least got to do it twice. And here's the reason why. From the initial to the first heating, did the amount drop? Yes. From the first heating to the second heating, did the amount drop? So would you continue heating? Did it drop from the second to the third? Yes. So would you continue heating? Yes. Now this last one looks a little weird. Why does it look a little weird? It went back up. But here's the bottom line. Do you think that could be due to a balance malfunction? Or to a slight alteration in the balance? Sure. But here's my major question. Did it stop decreasing? Yes. So could you say definitively that all of the water has been driven off by this point? Yes. Now, what would we love to have seen during that 4th heating? It stayed the exact same. Then you know, guaranteed. But I'm telling you now that don't freak if it goes up just a grunt. Okay, it might go up, it might go down, it just kind of depends. And here's why it could possibly go up. Because once all of the water has been burned off, is there other stuff in there that's burning? Could it possibly react and change the formula just a smidge? You may have 2 or 3 molecules of oxygen say, ooh, look, I'm hooking up with those, and stick to it. Could that bump the mass up just a grunt? So we're just going to pretend that all the water's driven off and everything has been perfectly stayed the same. If we could do this in a perfect world, we would do it in a vacuum, but you can't do that. So my question again one more time is, can you tell how much water has if all the water has been driven off. How would you be able to explain that with your mouth? Okay? After sufficient heating, did the masses stop decreasing? You can then assume that all the water has been driven off. We cool with that idea? So, the only thing left in that crucible after that fourth heating is what? Okay? We're going to assume that this is 100% CaCl2. 100%. True? Now here's my next question. What physically caused the mass to drop? The water. Can you determine how much water was boiled off? Yes. How would you do it? That was my next question. Which one do you use? I would say the least. So 4.72 minus 5. And this goes back to my question. What could have caused this to go up? That or something else reacting with it. So this is going to be our minimum number, so let's go with our minimum number. Okay. So what is 4.72 minus 3.56? Okay. So our grams of H2O was what? 1.16 grams of water. Okay. So we cool with that? Now, here's my next question. What is the only way to compare two different compounds? Their moles. So, we've got to get both of these amounts into our moles, right? So let's do that. So, I've got 1.16 grams of water, and I've got 3.56 grams of calcium chloride. So we've got grams into moles. We've got grams into moles. I know that this is 18.02 into 1. Calcium chloride is 110.98. 110.98 in 1 mole. That gives me 0.03, 0.0655, and 0.0321 mole. And I promise I'll move in a second. Moles of CaCl2. So, in essence, what are we trying to find? What was the question? How many waters were a part of this hydrate, right? So, now that we have these two things, can we compare them? I'm trying to figure out how many waters were in this thing, right? Okay? So what do you do with those two numbers? Divide the top by the bottom. Okay, so that's your formula. Now, if you did this backwards and you did moles of anhydrate over moles of water, what would your answer have come out to be? A fraction or a decimal? And you know you're wrong. You have to come up with a whole number here because you can't have half a water. No, you did it wrong. They're not going to give you a problem that gives you a decimal. Now, is it possible for it to come out to be 1? They could be the same. Don't freak out if it's the same, because it's possible it can be 1. It's rare, but it's possible. It is 2. 0.06 divided by 0.03 is 2. So, when we divide these numbers, we come out with 2 waters. 0.06 divided by 0.03 is 2. Okay. Now, my question to you is, at the very bottom down there in black, it says moles of water over moles of anhydrate. Why can you not do it in mass? Can you compare two different things in masses? You must compare everything in moles. Yes. Bingo. Yes. Yes. Okay. So, when we go back and we look at this, now we know that this is, by name, calcium chloride what? Very good. Dihydrate. It's the prefix hydrate. Yes, ma'am. That will be on a table. Do you remember when we saw the copper and the iodide thing, how it was listed in the table? It'll be the exact same thing. Where you have a mass after one heating and a mass after, they may only do 3 heatings. Okay? But they have to do something. But the whole thing that I need you guys to see out of this, and again, it'll be at a beautiful, pretty table, is that how can you tell with your eyes when all the water is gone? It stopped decreasing, and which one would you pick, the least or the most at the bottom? The least, because just in case something else reacted with it, you don't want to include that in your mouth. Yes, ma'am. Well, let's think about this. Let's say we did 10 heatings. Hypothetically, shouldn't that number after the 3rd heating never change again? So once you hit 2 numbers that are the same, do you want to keep heating? Just stop. You're done. So it's always going to be the bottom ones. And honestly, even if you kept heating, those numbers should be very, very, very similar. Okay? Does that make sense? Yeah, because there's something called overheating, which is essentially you decompose the entire compound, which is not good. Okay. All right, the last bullet. Okay. Explain how the following, gentlemen, okay, could affect the hydrate formula. Now let's pause there. When it says the hydrate formula, up there in that purple that you see written, what's the only part that you can really affect? The number of waters. Would you agree with that? So we're solely focusing on how could you affect the number of waters in a hydrate formula. Because is the calcium chloride going to change? No. But we're going to affect the number of waters. What would happen if you had too much heating? Okay. Could it... You could overheat. You could break it down. You could decompose the compound. Would that then decrease your moles of the anhydrate? Yes. Okay. Next one. Well, if you impact the moles of the anhydrate, does that affect your moles of water? Yes, or the number of water. What if you don't do enough heating? What does that affect directly? Okay. Does that affect the moles of the water? Okay, which tells you have too much water. Okay. What happens if it splatters the compound while heating? Be very careful. Okay? But can you assume that all of it that splattered was just the calcium chloride? No. So, would it affect both moles? Yes. So, would it affect your formula overall? Potentially, but what you're probably going to do is you're going to assume that it affected it equally, even though it didn't, and your answer is probably going to be the same. But it affects both moles equivalently. It hopes that it left, for every 1 calcium chloride, you had 1 water. You're hoping that's the case, but what's the chances of that actually being realistic? 0. Yes, sir. Yes, sir. Yes. I'm still thinking. So what would it be? How would it affect, like if it splattered out, how would it affect the mass of the water? Like how would it affect the amount of water that you had? Okay, so let's go back and look at this. If some splattered out, which trial changes? So let's pretend that it splattered at the very end. Would it affect that bottom number? Would it make it lower? If the bottom number got lower, what number got higher? The amount of water. Because you assumed that all of it was water in that case, right? And more of it burned off. So does that affect the mass of the water, which then tells you have more moles of a water, which means then it looks like you have more water actually in it. True or false? Does that make sense? Yes? It would increase the number of water because it looks like more water was driven off. All right, so let's pretend this. Let's pretend that bottom, that fourth value was 3.40. But when it went from 5.6 to 4.0, that was the compound and not the water. But what would you assume that it was? And that would have to be added to the 0.116, right? Or the 1.16, which then makes your moles of water go up, which then makes the ratio look larger than it really is. Does that make sense? Okay. Yeah. That's why you keep a cap on it. Okay? All right, so is everybody cool with that? Spectacular. We good? Yes. Words are very important. Yes. Would cause. All right. So that's pretty much the free response. Do you want me to go ahead and start hitting the multiple choice? We got 5 minutes left. Okay. All right. Well, I'll do this. I do want to do this one. Be able to calculate the relative atomic mass of an element from a mass number and a percent abundance. It's this thing. The average atomic mass is the mass that appears on the periodic table. Remember, you take the mass of the isotope and multiply it times the percent abundance, and then add all of those up. It's exactly like algebra. Now, this particular one, notice where the X is. Yes, we needed the mass of a specific isotope, which happened to be 74. Okay, but what if I said this isotope was 74? What's the average atomic mass? You would do the isotope times the percent plus isotope times the percent plus isotope times the percent. Add them all up, and that would give you 75.42. Because remember, if this is 30%, that is 67.6%. Do you agree that the higher the percentage, the closer the average mass should be? Okay, this is that first bullet. This is how you calculate it. Yeah, the top part. They have to add up to be 100%. Yes, sir. Yes, but that could be X. You may have to solve for that. I could give you the percentages for 3 isotopes. I could tell you what 3 isotopes it is and say, all right, what's this average atomic mass? And you have to do the isotope times the percents. Now, you do know that percents, you don't plug them in as the percent number, right? All right, so making sure we're all on that point. You move the decimal 2 places to the left. Okay, or divide by 100. All right. Be able to calculate the empirical formula for percent composition. Okay.